Okay, so as you guys saw from the packet, chapter 13 is all about vectors. We're going to do a whole bunch of stuff. We are going to graph some vector valued functions. We're going to talk about what that means. We're going to look at limits and continuity of vector valued functions. And then tomorrow we're going to do calculus of vector valued functions, so like derivatives and integrals and stuff like that. Sound good? I mean, you guys knew that was going to come, right? Like, it's a calculus class, so. First thing I want to review, and this is something we talked about last chapter, is parametric curves. So last chapter we looked at parametric curves, specifically lines. In 3 space and 2 space, parametric curves are going to look like this. X is going to be some function of t, y is going to be some function of t, and z is going to be some function of t. These are going to represent a space curve in 3 space. And of course, you could do the same thing in 2 space, but we're going to be looking at 3 space. Now, those equations represent a path in space that is traced in a specific direction as t increases. That direction is often referred to as the orientation. So we didn't focus too much on that, but as you plugged in your values of t, you got your curve in a specific direction. If you remember talking about the equations of lines, when you chose t values greater than 0, you were going to the right, whereas t values less than 0, we're going to move you to the left on your curve. Last thing I want to review before we move on is domain. Your domain is going to be all real numbers unless specified otherwise. Okay, so the whole reason we need to review parametric curves is it's going to help us with this first section, which is vector valued functions. So next thing we're going to talk about is vector valued functions. We are not going to write out a whole long definition. I'm just going to show you what's most important. Your vector valued function is going to be called r. Sometimes it'll be written as r of t. It's going to be a vector where the x component is defined by some function, the y component is defined by some function, and the z component is defined by some function. All 3 of these are called component functions. Of r. So here's what's important. At any given t value, r represents a vector whose initial point is at the origin, and then the terminal point is going to be the point f of t, g of t, h of t. So first thing that we're going to be interested in is graphs. So anytime you talk about graphs, of course, you're going to look at the domain and range. Domain for these vector valued functions is going to be all real numbers. Range is going to be a set of vectors. Most of the time, your domain is all real numbers. We're going to look at some cases where it's not. So in terms of a graph of a vector valued function, So from now on, I'm going to use VVF. That means vector valued function. The graph of a vector valued function is going to be a curve that is traced by connecting what I'm going to call the tips of the radius vectors. So here is an example. So with that r of t, what you're going to be doing is you're going to be plugging in different values of t. So let's say you plug in t equals 0. That might give you this little vector right here. So let's say that that's r of 0. So that's what I get when I plug in t equals 0. Then I might plug in t equals 1, and I might get this vector right here. And then maybe I plug in 2, and I get this vector over here. Okay, so then the graph of the vector value function is when you connect all of these tips. So it might be a curve like this. So we call that r of t, or just r. And then you put the arrows to show the orientation. So graph of a vector valued function is really similar to a parametric curve. It's still a curve and it still has orientation, just the way you graph it is a little bit different. How are we doing so far? Okay? Okay. We're going to do a few graphing examples and then we'll move on to our next idea. First example, this one is going to be in 2 space. R of t is going to be 2 cosine of ti subtract 3 sine of tj. And I'm telling you in this case that t is between 0 and 2 pi. So anytime you've ever learned graphing before, or you haven't known how to graph something, you've plugged in some points. So that's what we're going to do now. You're going to plug in some values of t. Those will give you an x component and a y component. So obviously you want to plug in 0 because that's where you start. Some good ones would be pi over 2, pi, 3 pi over 2, and 2 pi. If you plug in 0, cosine of 0 is going to give us 1 times 2 is 2. Sine of 0 is going to be 0. So that gives us the first vector. If we plug in pi over 2, cosine of pi over 2 is going to be 0. Sine of pi over 2 is 1, so that gives me negative 3. So these are the components of the vectors that we'll be graphing. If we plug in pi, we're going to get negative 2, 0. We plug in 3 pi over 2, we'll get 0, 3. And then 2 pi will give us 2, 0. Okay, so now we have to graph all of these vectors. First vector is 2, 0. That's that vector. 0, negative 3. Negative 2, 0, 0, 3. So what is this going to form? An ellipse. So this is where we started. So we're going to connect the points of our curves, or the points of our radius vectors, rather. You have to show the orientation, so we started here, heading this direction. Now, remember that those are just the radius vectors that we chose. If we plugged in other values, there might be a radius vector there, and there, and there, etc. So do we get how this works? If you wanted to think of it parametrically, it would be x equals 2 cosine of t, and y equals negative 3 sine of t. So that's the same function, just represented parametrically. Ready for our next graphing one? Okay, good. This one's in 3 space, so hope you're ready for that. Okay, next example. R of t is going to be 4 cosine t, comma 4 sine of t, comma t. Now, we should have some idea of what this is going to look like. If we do it in 2 space, 4 cosine t, 4 sine t, based on the last example that we did, what do we think this will give us? Circle. What happens when you introduce that z of t? It's kind of a cylinder. It's like a circle that's opening up, like this. Kind of. We'll graph it, but that's a circle, but it's going to be moving up also. Okay, so same thing from before. Plug in values of t. We're going to plug in all the same ones we did before. So 0, pi over 2, pi, 3 pi over 2, and 2 pi. Okay, can I trust that you guys can plug these in? So can I just write them all down for you? I'm going to read you the x column going down. 4, 0, negative 4, 0, 4. The y column is going to be 0, 4, 0, negative 4, 0. Z column is going to be 0, pi over 2, pi, 3 pi over 2, 2 pi. Okay. You all know from our last chapter that I am not a good artist. So go with me a little bit on this one, okay? I don't want to hear any comments about how my drawing sucks. Okay. Okay, so first point, 4, 0, 0. It's going to be that one right there. Then we have 0, 4, and pi over 2. Okay, so 0, 4, pi over 2 is about there. Then we have negative 4, 0, and pi. Okay, here's my suggestion here. Pi 3.14 is about here. I would move another dotted line out so that you get the perspective right. So 0, or rather negative 4, 0, and then pi, that's about there. Bless you. Okay, and then we have 0, negative 4, 3 pi over 2. 3 pi over 2 is about 4.71, which is about here. Okay, and then, so let's start by connecting those. And then there will be another point about there. So do you see how it's a curve wrapping around a cylinder? So it's helpful maybe to... I really feel like this drawing's not that bad. It's not, guys. Yeah, it's like a slinky. Yeah, it's a slinky. So it's like this. Like if you draw on a cylinder, the cylinder is not part of the graph, but the graph is wrapping around the cylinder. Alex, where am I losing you? You're looking at me like I'm crazy right now. Okay, you got it? We good? Okay, if you want to see the drawing on my notes, which is a little bit better, looks like that. So we have the cylinder, we're wrapping around it. You guys with me? Okay, great. Good news for you is that WebAssign obviously can't force you to sketch anything. So on WebAssign, it's going to be more of, here's the vector valued function, pick the correct graph. In your packet, though, it will make you sketch. Questions on graphs before we move on? No. Great. Here's our next example. And this is something that we've done before, so this is not going to be new, this next one. Find a vector and parametric equations for the line segment that joins A, which is the point 1, -3, 4, to B, which is -5, 1, 7. Okay, so we did this last chapter. We talked about if you're writing the equation of a line, this is a segment, but it's the same idea. You need a vector parallel to your line, and you need a point. So we obviously have a point. We have 2 to choose from. How are we going to find the vector? Yeah, find the vector joining A to B. I'm going to call that vector R. So really what I mean is AB. -5 minus 1 will give us -6. 1 subtract -3 is going to give us 4. 7 subtract 4 is going to give us 3. So then our R of t, these will be the slopes. I decided to use the first point. So we get 1 subtract 6t, -3 add 4t, 4 add 3t. So that's the way to write it as a vector function or a vector valued function. If we decided to write it parametrically, x would be 1 minus 6t, y would be -3 plus 4t, and z would be 4 plus 3t. Now, that's a line. How do we make it a segment? Restriction. And how do we restrict t? 0 to 1. And this applies to both the vector valued function and parametrically. If you plug in 0, you're going to get point A, since that's when we started. If you plug in 1, you'll get point B. Okay. Questions before we do another example? No? Okay. Find a vector function that represents the curve of the intersection of the following 2 equations. First one is going to be x squared add y squared equals 1. Second one is y plus z equals 2. Okay. If we were to graph this first one, the x squared plus y squared equals 1, what is that going to look like? Cylinder. So this one will be a cylinder. Y plus z equals 2. That one's a plane. Okay, so we're taking a plane, we're taking a cylinder, and we're going to intersect them. First thing that we're going to do is we are going to start with that x squared plus y squared equals 1. And what we want to do is write that parametrically. Do you guys know how to write x squared plus y squared equals 1 parametrically? Think back to this example that we did. We talked about if you take away the t, what are you left with if you were just to graph that? Yeah. Remember how we talked about this as a circle? When you put the t in, though, it makes the circle open up. It's not really a circle anymore, but that's the idea. Okay, so for example 4 then, x is going to be cosine t. Y is going to be sine of t. Parametrically, that'll give us a circle. T is going to be between 0 and 2 pi. Okay. So that takes care of x and y. We need z now. Sorry, y plus z. So if I solve for z, I get 2 subtract y y is what I have up here, that's sine of t. So now I have a parametric expression for x, y, and z that takes both figures into account. So our curve then, we want to write it as a vector valued function. X is cosine of t, so we get cosine of ti. Add sine of tj. Add 2, subtract sine of t, okay, with t being between 0 and 2 pi. So that's the equation of the intersection of those two figures. Questions? Okay, that's not the only option. What you could have done is you could have solved for x or y, either one, and you would have gotten x in terms of y, and you could have then plugged it in. Does that make sense what I'm saying without writing it down? Okay, so sometimes what people do, like another option, if we did it over here, maybe you choose x to be t. So then if you solve for y, you would get y equals plus or minus the square root of 1 minus x squared from here, and you could then plug in t. Same thing here, you would solve for z, you would get 2 minus y, and then you would have to plug in your expression for y. With me? Okay, that just does not look as nice. So you could do it that way, totally fine. It's just not gonna look as nice. There's some that's gonna be the best option. If you're curious, this is what those figures look like. So here's the cylinder, here's that plane, so you're left with an ellipse. So this is the equation that we just wrote. Kind of cool, right? You guys like don't have too much energy today, do you? Are you guys more excited by the storm than by my notes right now?
The lightning is pretty cool.
The lightning is cool? Math is cool too.
Lightning is a...
Okay. 2 other things we need to talk about. We're going to talk about, well, 3 things. Domain, limits, continuity. So, our domain example. We are going to find the domain of r of t. R of t is going to be in 3 space. The first component is the natural log of the absolute value of t minus 1. And then e to the t is the second component. Third component is the square root of t. Okay, here's what I mean by domain of a vector valued function. Domain includes all values of t for which r is defined. So the basic idea is you're going to have to treat all 3 domains separately, or all 3 components separately. So x, y, and z. Okay, y is the easiest. E to t. For e to t, what are the values of t for which that function is defined? All real numbers. So based on y, t has to be a real number. Based on z, so the square root of t, what values is for what values of t is that function defined? Greater than or equal to 0. Okay, how do we approach the natural log of the absolute value of t minus 1? I don't want to know the domain right off the bat. I just want to know, what do we need to consider? What do we need to think about first?
Natural log will be negative.
Okay, so we know that natural log, you can only have positive numbers.
Yeah.
So anything bigger than 0. So we need the absolute value of t minus 1 to be greater than 0. Do you remember how to approach problems like this? Okay. when are we going to be equal to 0? Let's consider that. When t equals 1. So this is what I would do, is I would consider a number line. When t equals 1, we get 0, which we don't want. When t is greater than 1, is that good? Is that part of our domain? Yes. When t is less than 1, is that part of our domain?
Yes.
Yes. So any number is okay except t equals 1. The domain here is going to be negative infinity to 1, union 1 to infinity. So then the overall domain is going to be the intersection of all three of those. So that one's not helpful, so we can ignore that. So we need this to be true and t to be greater than or equal to 0. So our domain then is going to be 0 to 1, union 1 to infinity. Does that make sense? So consider all three domains separately and then find where their intersection is. Okay, we got one more page of notes, like probably 10 minutes. Last thing we need to talk about is limits and continuity. Starting with a limit. Consider r of t to be a vector valued function with the components or component functions f of t, g of t, and h of t. Then the limit as t approaches a of r of t. The way you find that limit is you find the limit of each of the component functions. So you're going to have the limit as t approaches a of f of t, the limit as t approaches a of g of t, and then the limit as t approaches a of h of t. And that is as long as all three limits exist. So here's an example. We are going to let r of t be t squared I, add e to the tj, subtract 2 cosine of pi t k. We are going to find the limit as t approaches 0 of r of t. Okay, so if I want to find the limit as t approaches 0 of r of t, I have to take the limit as t approaches 0 for each of the component functions. So this is going to be, I'm going to write it differently. The limit as t approaches 0 of t squared, whatever that is, multiplied by I. The limit as t approaches 0 of e to the t, multiplied by j. And then the limit as t approaches 0 of 2 cosine of pi t, all of that times k. Limit as t approaches 0 of t squared, that's just 0. So we get 0i. If I plug in 0, that ends up being 1, so plus 1j. If I plug in 0, cosine of 0 is 0 times 2 will give me negative 2. You don't need to write the 0i. I just wrote it to help you know where it came from. Questions on limits before we do one more example? Am I going too quickly for us? No, we're okay? Okay. Next example. R of t, the first function, is 4t cubed plus 5 divided by 3t cubed plus 1. Second function is 1 subtract cosine of t over t. Third component function is the natural log of t plus 1, that quantity divided by t. We're going to find the limit as t approaches 0 of r of t. Okay, so the limit as t approaches 0 of r of t. I'm not going to write out all of that again. Is that okay? You just know that you're looking for the limit of each component function. If we plug in 0 here, we're going to get 5 over 1, which is 5. If we plug in 0 here, that'll give me a 1. So 1 minus 1 will give us 0, divided by 0. Plug in 0 here. Oh, look, we get 0 divided by 0 again. What do we have to do? L'Hopital's rule. Remember, L'Hopital's is also when you have infinity over infinity, or plus or minus infinity over infinity. Okay, so take the derivative of 1 minus cosine t. What is that? Sine t. So we get sine t over 1. Derivative of natural log of t plus 1. 1 over t plus 1. And then the derivative again gives us 1. Now we can plug in 0 again. If we plug in 0 here, we get 0 over 1, which is 0. If we plug in 0 here, we get 1 over 1, which is 1. Okay, how do we feel about limits? Good? All of this should be fairly intuitive because it's stuff that you've done before, just applied in a different manner. Last thing we need to talk about is continuity. A vector function. When I say vector function, that's the same as a vector valued function. So just know those are the same. Sometimes we leave out the word valued. A vector function, r of t, is continuous at t equals a, if and only if. Do you guys remember when something is continuous?
So like the limit as t approaches a from the negative side equals the limit as t approaches a from the positive side equals what was the last one? Equals when you just plug in a to a function.
Yes. I'm going to write it differently. If the limit as t approaches a of r of t is equal to r of a. So Alex was saying as the limit as t approaches a from the left and the right are the same, that means that the limit exists at that point. So that's the other way of writing it. Okay, looking at example 6. Is r of t continuous at 0? So is the limit as t approaches 0 of r of t the same as r of 0?
Yes.
Yeah, right? We just plugged in 0 for all three functions. So this example is continuous at t equals 0. Example 7, are we continuous at t equals 0? No. No, and that's because of the L'Hopital's rule that we had to do. Questions on vector valued functions?